Hello, welcome back. This is week 6 of Graduate Statistics, University of Cincinnati, and this is video lecture 3. So we have just solved a problem. We needed to compare the score that Pam got on an SAT score with the score that Jim got on an ACT, the score that Pam got on an SAT exam and the score that Jim got on an ACT exam. And we used standardized scores that reflect how many deviations above the mean each one of the students or the candidates or the applicants scored. So this is sort of an intuitive introduction to something I am positive you've seen before if you took statistics, which is the idea of standardized or Z-scores, right? Z-scores, people typically know how to compute them. They learn the formula, but they don't know why it is used. That's why I'm doing this introduction kind of slowly to try and remediate that. Remember, Z-scores are used to put scores in context when you have to compare values that are coming from distributions that have different means and standard deviations. So one more time with feeling. Standardized or Z-score of an observation is the number of standard deviations it falls above or below the mean. Because we subtract the mean from the score, if the Z-score is positive, it means that it represents a score that falls above the mean. If the Z-score is negative, it represents a score that falls below the mean. Here you go. If the observation is bigger than the mean, the Z-score will be positive, and that will indicate in the case of an exam score, it indicates a good thing. It falls above the mean. If it is, I don't know, you're measuring the time people took to run a mile, and it's a race, being above the mean, having a positive Z-score, is kind of bad because higher values of time indicates worse performance. But you have to know that positive Z-scores means that a particular variable score on a variable fell above the mean versus a negative Z-score, that value fell below the mean. So what is the Z-score of the mean then? Let's check your understanding. This is the formula. And we talked about that on the previous video, but let's get that hammered in. If somebody scored at the mean, if somebody took the SAT test and scored at the mean, what would be the Z-score? 0, right? The SAT score, the mean is 1500. If we subtract the mean from that score. If I scored 1500 and the mean is 1500, 1500 minus 1500 is 0. 0 divided by anything is 0, right? So the Z-score of the mean of a distribution is always 0. What range of Z-scores would you say refer to an unusual observation? Think about the rule. The 68, 95, 99.7 rule. Scores that are above choose standard deviations, because then they are starting to fall, toward the tails of the above or below, because then they are close to the tails of the distribution, right? Very good. Note, Z-scores can be defined for distributions of any shape, but can only be used to compute the percentiles when the distribution is normal, because it's only when the distribution is normal that the 64, 80, 95, 99.7% rule applies, right? So you cannot guarantee that one standard deviation above the mean will fall on the percentile, on the 84th percentile, if the distribution is not normal. Yes? Okay. So I cannot say here, for instance, that being one standard deviation below the mean, that this will be the 16th percentile, right? Because I cannot guarantee that 64% of the scores will fall in here, all right? So that's why if you're going to use the z-scores to compute percentiles and probabilities of scores, you need to do so. You can only do so if the distribution of the scores you're looking at is normal. That's why at the beginning we said you need to know the mean, the standard deviation, and the distribution shape, right? To use z-scores, you need a normal distribution. All right. Computing percentiles. We mentioned that percentiles represent a score that is above a particular percentage of scores. So if my kid goes to the doctor and the doctor says, oh, she's in the 70th percentile of heights, that means that 70% of the kids are her height or shorter, right? If somebody tells you that your salary is on the 30th percentile of all people in your area, you would be like, is there something wrong? Why are they paying me so little? Should I go somewhere else and find a job somewhere else, right? Because if you're in the 30th percentile, that means that 30% of the people that in your profession make that amount or less, okay? So we compute percentiles because they put scores in perspective. If somebody gives you, said, is a salary, if you're thinking about salary, let's go back to that. Is that good or bad? Of course, there may be objective ways to look at this, but if you have a given profession, like I'm a professor, there's only certain expectations I can have about my salary because of how salaries are paid in universities. So to know if I'm being well paid by my university, I can't compare with the salary that, I don't know, surgeons make or that politicians make. I don't know. I have to compare with my group of people, and percentile kind of helps with that. SAT scores are distributed normally with mean 1500 and standard deviation 300. Pam earned an 1800 on her SAT. We talked about that, and that's one standard deviation above the mean. What is Pam's percentile score? And what we can do is first compute the z-score, which is 1, and then compute the probability that z is less than that value, right? Isn't this what a percentile is? The probability that somebody makes, reaches that score or lower, right? So it's the probability of having a z less than 1. So it's the probability is 0.84. That means you're in the 84th percentile. You can expect 84% of people to score below 1. And typically we can use tables to find that. So remember, probably when you're doing statistics, if you use SPSS, you had to refer to tables sometimes, especially at the beginning of the course. You have z here. The z equals 1, where these two things cross, you have the probability of finding that score or lower. Sorry, I went too quick here. And here's how we represent that, right? So 1800 is right here, and we can expect that 84% of people score below that. The probability, it's equal to saying that the probability of scoring below that is the area under this curve here, this probability curve. Remember, the normal distribution is a probability distribution. The area under the curve tells you what's the total probability of getting that score or lower, which we got from the table. Now, if you want to know the probability of getting that score or higher, you just get 1 minus, because you want the upper tail, right? You get 1 minus the percentile, and then you would get the probability of getting that score or higher. It's only 15-16%. Still typical, as we talked about, but it is 16% chance of people getting it, so not very high, which suggests it's a good score to get. Even though I showed you these ways of computing the z-score, this way of computing the z-score, the percentile, which is to compute the z kind of by by hand and then looking at a table, you don't need to do that because we're using R. We are going to do it in a much simpler way using the function pnorm. It's the probability under the normal distribution of a particular score, 1800, if you are comparing it to a distribution of mean 1500 and standard deviation of 300. So by using pnorm, you'll use that in the lab, you will see that it needs 3 parameters: the score you want to classify, get the percentile of, the mean, and the standard deviation. When you say nothing, the default parameter is that you're getting the probability of the lower end of the distribution, right? The lower tail of the distribution. So if you say nothing, R assumes that you want the lower tail. If you want the upper tail, it's all good. You do exactly the same, and then you see in the lab that we just have to add 1 parameter and say upper tail, lower tail equals false, because we want upper tail. And upper tail is set to, lower tail is set to true when you say nothing. So here is the 84 percentile right there. Okay? Awesome. Let me see where I can position myself. Now, a friend of yours tells you that she scored in the top 10% of the SAT. What is the lowest possible score she could have gotten to be at that percentile, right? Let's go now from, we went from score to percentile. Now we have a target percentile and we want to know the score, right? Because perhaps you only know your score, so you know, did this person score more than me or less? You can go back to the score and figure that out. So it's always useful to draw. So when you're doing the activities in the lab, make sure you have a sketch pad by your side and you're sketching these distributions to figure out what you're looking for. So we have a normal distribution again, and here's what we want to know. We know that it's in the top 10%, so we know that the area under this curve here, the probability of the area, the upper tail, is 0.10, but we don't know what the score is. So how do we figure this out? Well, there is a function that can quickly get you first the z-score that then you can use to get the probability. You can come here and use qnorm but to get the z-score, because you just say, oh, by the way, I want the z-score that relates to the 90th percentile, which you know that's what you need, and you get the z-score. And if you know the z-score, and you know the mean and the standard deviation, which we do, of the SAT test takers, now the only unknown is the observation. So you can compute that by doing those steps. Now, how do you compute that? Just set up the equation, right? So you have 1.5, have the z-score equals 1.28 right here, and that's equal the unknown, the thing you want to know, which is the observation, what is the score that the person got, 1500 divided by 1500 is the mean of the SAT test takers, and 300 is the standard deviation. By solving this equation, you know that her score was 1884, so greater than the score that Pam got. As you can imagine, we don't need to do these calculations by hand. We can use qnorm, extended. You don't need to get like this intermediate z-score. R will do everything for you in the background. All you have to do is pass the percentile, the mean of the test takers, and the standard deviation of the test takers, and R will output for you the score, right? So we use pnorm when we want the percentile, and we use qnorm when we have the percentile and we want the score. So this is it in terms of video lectures. I hope this information will be helpful for you to follow along the guided activity and the independent activity. All right? Bye-bye.